The swing ride has been around roughly since 1908. There are many versions of the ride all over the world. The one we chose, the Wave Swingers, was designed by the company Zira and built by a German man, Franz Squikowski, in 1972. The ride is mostly made of steel, chains, and cables. You sit in a chair and the ride rotates so you swing out. The top of the ride also tilts from side to side, which causes you to swing higher and you to swing out farther. The ride seats roughly 42 people and runs roughly 12 hours a day. One person a cart, and all at the same time.
When analyzing the physics of this ride, we first had to start by taking measurements. We started with the height. For this, we basically made an imaginary triangle by measuring the distance from the center of the ride and measuring the angle here so that we could solve for this distance from here. We also had to find the distance traveled, which means that we had to find the radius for full rotation, and that was what we also had to use. We had to use the radius, and then we had to use that to find the total distance traveled as they go around the track. We also had to find the potential energy, so we had to measure the weight of these carts and the height from the ground so that we could calculate that. I think that's it.
First, we had to calculate the height of our ride. To do this, we use this formula. So if this is our ride, we had to calculate the angle from which we were standing and the distance. From the distance, we simply just measured from the base of the ride all the way to where we were standing. And this equaled out to be 45 feet. Next, we had to find the angle. To do this, we used this tool, and we pointed it up to the top of our ride and then measured the angle. This came out to be 36 degrees. Okay, then we just plugged our numbers into the formula. We did this is just height equals the distance, 45, tangent of 36. This, when we plug this in the calculator, we got the height equal 33 feet.
Next, we had to find the average speed, which is the total distance divided by the total time. The total distance we found to be 19.1 meters, and the total time we found to be 165.9 seconds. Which, once it was divided, our final answer was 0.114 meters per second.
After finding the average speed, we had to find the instantaneous speed at the fastest speed of rotation. So we plugged in our short distance, which in this case was half a rotation, and divided it by the time it took to go that distance, which was 4.77 seconds. And then when we divide that, it comes out to 2.1 meters a second.
Hey, boss.
We also had to find the potential energy of the carts. So we use this formula here. Potential energy equals mass times gravity times height. So when we plug in the numbers, we get 64 kilograms, which is the mass, times 9.8 meters a second squared, which is the acceleration caused by gravity, and 3.4 meters, which is what we estimate to be their height above the ground. So we multiply this all out, we get 2,100 joules.
Find the half speed of the rotation through distance over time. We calculated the distance to be 56.5 feet and the time to be 10.5 seconds, which is 5.38 feet per second.
Okay, the formula for speed doesn't change. So for full speed, we do the same thing as we took the calculations when it was at full speed, which would be, it was 62.8 feet divided by 7.2 seconds. Came out to be 8.72 feet per second.
Next, we have to find the angle of rotation, which is found by the formula. The angle equals the arctangent of 4 pi squared times r divided by gravity times time squared. So we start by plugging in our numbers.
Can I just say that's a mouthful?
Our radius is 3.05 meters. The acceleration due to gravity is 9.8 meters a second squared. And the time was 7.2 seconds squared. So now we just type this in our calculator. We find theta to be 13.6 degrees. Go.
Okay, last thing we had to find was centripetal velocity. And here's the formula for centripetal velocity. And we just plugged our numbers in that we found, and what we had was 2.1 meters per second squared over 3.05 meters. This is what your centripetal velocity equals, and we plug this in, we got 1.4 meters per second.
The figures used in the physics analysis are estimates and not exactly correct. For instance, the potential energy is not entirely accurate because the numbers we used were estimates because of our group's inability to measure the necessary aspects of the ride. Instead, they are estimates, which means the calculated potential energy is an approximation instead of an absolute answer. We realize from this why significant figures are important. Since it is rarely possible to measure something exactly, the answer must be good of an estimate as possible.